Nice to see everyone. So today, a bit of a broad topic. I'm going to try and sort of zoom through the entire supply chain from atoms to tokens. Very, very ambitious. I think I have way too many slides, but I'll get started, right? So when you're talking about, we're at Design Automation Conference, the first, major change that everyone is seeing all the way down at the atom scale is in the front end, right? Interconnects are not scaling. They've scaled quite slowly. The last inflection, really major inflection, was going from aluminum to copper in 1998. Since then, there have been attempts to move away from copper. Intel tried to go to cobalt for their interconnects on 10 nanometer, and that completely failed. And so they had to go back to copper. Now, though, there's a lot of different avenues for scaling and attempts to scale. The use of tungsten is already being done in contacts and vias. And additionally, molybdenum and ruthenium are being attempted for future generation nodes, really around this 1.6 nanometer or so era. The interesting thing is the process for manufacturing this is entirely different, right? Instead of the typical dual Damascene process, which is sort of pictured or has been used for decades now, there are subtractive processes, which means the design rules for your metal interconnects are going to entirely change. And furthermore, it's really, really relevant because interconnect scaling is what's limiting AI chips, right? While mobile chips and other lower speed chips don't care as much about interconnect performance, AI chips care a lot about them. And this is sort of the same thing with backside power, right? So far, all power delivery and signal has been on the front side. Soon enough, in the next couple of years, we'll start seeing chips in high volume production with backside interconnects. And this is really relevant again because again, not necessarily that important for mobile, but for AI chips, high performance chips where speed matters, where power matters a lot, there's significant movement there. And so there's a variety of different ways to do it. The way TSMC is doing it, Intel are doing it are different, but regardless, this is a massive change in design. It also means that you're manufacturing for test, you're designed for test. As you're going through the manufacturing process, because there's metal on both sides of the wafer, you can't test and do your metrology as easily. So that's something that's really important. Another aspect is a lot of folks have been counting on high-NA EUV coming to market, simplifying design rules again, right? With 7 nanometer, or with 6 nanometer at TSMC, the design rules were much simpler versus 7 nanometer where they had some quad patterning and such. And likewise, it got more complicated again with 5 and 3. And 2, but everyone was hoping high-NA EUV would come and greatly simplify the design rules for leading-edge semiconductors, but that's not the case because high-NA is very slow to adopt. TSMC has plainly said they're not going to adopt it. I can freestyle. Cool, I can freestyle. But TSMC said that they're not going to adopt it for a while to come, and that is very concerning because it turns out that multi-patterning with EUV is more cost-effective than single patterning with EUV in many, many cases. And then there's another aspect, right? If lithography, you're not getting the shrinks from lithography alone, there's other methods to do that, right? So there's scaling boosters such as pattern shaping. It's basically just like beaming ions at the wafer in a direction, and this changes the shape of the pattern that you've made with lithography. And so why that's relevant is you get different designs in terms of your contacts, your vias, your interconnects, and which again significantly changes the design rules, right? Trying to tie this back to this conference. And likewise, DSA, it's basically like you print a line and then it turns it into 2 lines. This again it's directed self-assembly, another method where your design rules are going to change significantly to continue interconnect scaling. And what's interesting about DSA is Intel said they're going to adopt it at 14A. Obviously, there's a lot of turmoil with what's going to happen, but that dramatically would save costs. Another area is packaging, right? the trend line of Moore's law in terms of cost per transistor has not been improving, but total number of transistors per package has been skyrocketing. And there's a number of different ways to do it. There's traditional sort of packaging on substrate. There's 2.5D packaging, where you're going through an interposer, silicon interposer, and now people are going to moving from silicon interposers to RDL interposers, or even local silicon bridges in an RDL interposer. There is some scaling there, right? Most standard chips have 130 micron bit pitch, but within the silicon interposers, we're getting down to 35 micron for next generation designs. So that's roughly 8x density increase. And these packages are getting much larger, but more importantly, some interesting things are happening with regards to the sizes of packages, right? With these packages getting 5x, 6x, 8x reticle sizes in design, fitting them on a 300 millimeter wafer is like kind of impossible, right? Fitting very large squares on a circle, tough. So the industry is moving to these panels, large format panels, which have been used for substrates, but not for advanced packaging. And Intel has panel level format work. TSMC has panel level format work. There's various companies like Silicon Box and others who are trying to do large format panel packages, and that is really transformative. As even Rubin today, their interposer is going to be 60 by 67, but there are chips in design with interposers that are 100 by 100. You could fit like 5 of them on a silicon wafer, so that's going to be ridiculously costly. Or if you fit them on a panel, that'll be much better. The other area where packaging is really evolving is hybrid bonding. You're doing copper to copper interconnects. The bump pitches are scaling really fast. It's not just chip on wafer. There's also wafer on wafer stacking that's happening. And then the most exciting thing that TSMC sort of has announced and been pitching to customers more recently is a system on wafer, right? They've pitched system on wafer in a integrated fan-out fashion where it was chip first, but now they're pitching a chip last system on wafer, which makes integration with DRAM and other things much easier, right? So currently, Tesla has the Dojo chip, but there's no DRAM on the wafer because of the manufacturing flow. But with TSMC's chip on wafer, system on wafer with chip last, you can add DRAM and other heterogeneous devices onto this very large format package. And so there's multiple designs in flight with this. Tesla, of course. Google's got projects, and numerous other companies have projects for literally wafer-sized chips, but done in a way that is chip last, i.e. you can test the chip before you bond it onto the wafer. The really, really key thing here is mobile the 2010s were all about PC, 2000s were all about PC, 2010s were all about mobile, but now all of a sudden mobile hit a real inflection point, right? Apple, a couple years ago, stopped changing the newest chip to the newest node. They actually started doing split. Only the Pro models got the newest phone. That's because the nodes started to get too expensive, right? With wafers getting to $20,000 plus per wafer. And smartphone unit volumes have actually started falling. They peaked at 1.4 billion, now they're at 1.2 billion. Apple, in fact, doesn't even want to use TSMC's A16 node, which is really, really scary, right? If the biggest customer doesn't want to use the newest node, in a couple of years, then what's going to happen? But thankfully, sort of AI HPC has really taken off. There's a significant number of tapeouts that are happening. TSMC has 5x the tapeouts on A16 that they do on 2 nanometer and 3 nanometer. And so while mobile has really fallen off, there is a whole new class of AI chips coming, right? Apple's first 2 nanometer chip or at least one of their first tape outs, is a accelerator they're making for their data centers, right? So something that the consumer won't even touch. And this is across the whole slew of all the hyperscalers and AI chip companies also just moving really rapidly to the newest node, which is enabled by advanced packaging, right? Because before, yield curves meant that you couldn't make these really large chips on leading edge semiconductors, but now you can. And so the HPC, we project the HPC industry will probably overtake mobile on leading edge wafer starts in roughly 3 years. So 2028-ish, maybe 2027 in fact. The other area that's really, really important is memory, right? Everyone knows about the memory wall. You've attended 100 presentations that mention the memory wall. So I don't specifically have that slide that has the memory wall. But the simpler premise is DRAM density is not shrinking, right? And so, we've gone to this extremely costly method of stacking DRAM, but the cost of DRAM there is, on the range of $15 a gigabyte, right, versus $3 a gigabyte for commodity DRAM. It's far too expensive. And then every other form of memory has real significant problems with regards to edge area, right? It just takes too much edge area on the chip, so you can't have high-speed I/O, networking. You can't get enough bandwidth. So if you want terabytes a second of memory bandwidth, you either just have to give up on all your networking capabilities, or you have to go to this extremely costly HBM. There is, so HBM stacked memory, it's very costly because the stack yields as you stack these dies. But the interesting thing is what's happening with the future of HBM, right? So HBM4, very, very simple. Due to the packaging advancements, they're able to double the bus width. But more importantly with HBM4 is that memory is for the first time becoming not a commodity, right? And what I mean by that is before memory was always, everyone can buy the same memory and integrate it, JEDEC standards, great. With HBM4, almost no one is following the JEDEC standards, which is really interesting that there's no standard, but it also means that memory is no longer a commodity, right? The DRAM makers are now having to turn to TSMC to get wafers from them for the base die. And in this base die, they're putting custom logic that their customers want, right? NVIDIA's not using standard HBM4. They're actually going and getting specific optimizations in their base die. But this now means that they have to do a separate tape out with each individual memory maker. And that memory maker can't turn around and take the memory that they sell to NVIDIA and go, oh, AMD you want some, or Google you want some, because it's tightly integrated. And there's some aspects of offloading memory controllers, or rotating tensors within the chip. There's also the idea of putting memory controllers inside the HBM base die, not for HBM, but for LPDDR. So you can actually stick memory behind the HBM, right? So if you look at a classical package, this is sort of what AMD's next generation chip is going to look like, but the top and bottom are reserved for networking, high-speed SerDes for chip-to-chip communications, and then the right and left are HBM. That's typical of every design, but behind the HBM, actually, they've stuck a memory controller in the HBM base die that lets them go to another tier of memory, which is LPDDR. And NVIDIA is doing the same thing. This enables you to have sort of flexibility on, hey, how much capacity do you want? You're going to have all the bandwidth, but how much capacity you want? And this is useful for things like KV cache offload. Another aspect that companies like Google are investigating is not doing memory controllers in the HBM base die, but actually a short die-to-die that takes you onto the substrate, and then on the substrate you have high-speed networking chiplets, right, for SerDes, right? And therefore you're not just limited to the top and bottom for high-speed SerDes, but actually you have the entire edge area of the sides of the chip, the left and right. Which then makes sort of, hey, I can 3x the amount of network I/O while still retaining all my memory bandwidth from my chip. And so this is sort of, again, each of these designs would be independent of the foundry, independent of for the customer, and therefore there's no cross-selling ability, and HBM is no longer a commodity. And then there's bufferless HBM and cache DRAM, which again is like 3D stacked DRAM. The TSV grids will be likely highly customized because it's going to be per chip basis. So again, the supply chain gets a lot more difficult for the DRAM makers who are used to making 3 or 4 designs a year, right? A couple LPDDR, a couple DDR, a couple HBM, that's it. Now they're going to have to make dozens. And so it's a big transition for them, especially in the EDA space where they're not used to actually having adopted all the EDA tools. It's actually a big opportunity for EDA tooling companies. Another aspect of this is the NVIDIA's Tensor Core architectural evolution. In the last 10 years, it's the biggest evolution in sort of computer architecture, in my opinion, right? And the problem is quite simple, right? Memory bandwidth is like this, but compute requirements are skyrocketing, right? And so what do you do, right? There's the programming model especially has turned to what's called asynchronous execution, right? Instead of, you load, you compute, you actually have different stages where you can load the memory, load a tensor or weights into a certain array, and compute separately, so you're always ping-ponging around. This is very difficult, and this is not the standard GPU programming model, which is parallel execution, and sort of, it starts to become more like a data flow, right? And that's sort of what NVIDIA has implemented on the latest Blackwell generation. There's actually 3 separate memories for each tensor core, right? There's memory within the tensor core, there's the reg file, there's the shared mem. And you're asynchronously loading and computing data, and this starts to look a lot more like a data flow, which is very interesting. I think and it feeds back into itself, right? The faster GPUs are being used to make masks much faster, right? So when you're in a lithography tool, you have your design, goes to GDS, you get turned into masks. You have all these patterns that you want to draw, but actually, like, if you want to make a line is not the best way to do it. Actually, you want to like do other patterns, because the interaction of the light through the tool and through the mask and so on and so forth, through the photoresist, you actually want to like not do exactly that. So there's inverse lithography, ILT, and all these other technologies where, if you're making vias, actually you shouldn't just have holes. You should have all these other weird shapes. And GPUs are being used to accelerate that, which means the time to make masks, the throughput of these lithography tools, all these things get better. So it's sort of interesting that it's a circular loop. And the same applies to AI chip design, right? Which is probably what this conference will be. The sort of star of this conference is the dozen new AI chip design companies out there. Very exciting work being done there. It's probably the most complicated problem humanity has, right? Let's organize 100 billion transistors and all the vias and contacts and metal interconnects perfectly to sort of do whatever architecture we want, right? And also the heterogeneity of architecture that's coming. And so it's an infinite design space, right? Because you can place these 100 billion transistors in many different ways. And so that's becoming a very difficult problem for the sort of labor force. Design timelines would extend if we didn't have really high leverage of EDA. Also, at the same time, the talent pool of chip designers is actually pretty much flat over the last decade. At least in the Western and in sort of the American fabless design companies, but the complexity of their designs is skyrocketing, right? So there's all sorts of interesting examples, right? Google's Alpha chip, where they use reinforcement learning to reduce the total wire length by 3.2%. Actually, a lot of power versus human experts. And then NVIDIA's Grace Hopper, they talked about how they had 13,000 AI-assisted chip design circuits. There's various agentic EDA workflows where people are creating their verification or test via with AI. There's all sorts of things with regards to contacting across a massive organization, because teams are very disparate. And there's all sorts of stuff all the way from generating Verilog to verification. There's really a lot of different areas where AI is being used in chip design. And so, it's not a question of like, hey, what can this do to help me save time? I literally won't be able to design my next chip if I don't start adopting these technologies. And because the design space continues to grow exponentially, especially with chiplets and package sizes growing so fast, your power is going to start to balloon. Your ability to close timing, do power delivery is just going to be way too hard if you don't start adopting these flows. And so Google, NVIDIA have talked a lot about this. AMD has some papers that have been very interesting. So Broadcom as well. And then Cadence and Synopsys, I think if for those who have sat in their sales meetings, they just want to push this all the time. And then there's the whole host of all the other companies out there. The interesting thing is the sort of base frontier models are actually decent enough to do like 16-bit adders now, which is really, really simple, to be clear. A good chip designer would be able to do that in their sleep, but they're starting to get like decent enough that you can start to design very small parts of the flow. The other area where there's a lot of changes is networking and optics, right? The big thing going on currently is the 100 gig to 200 gig transition. In this year, NVIDIA started shipping their first 200 gig chips, Blackwell, as well as the new InfiniBand switches. Interestingly enough, they've had tons of manufacturing challenges with the OEMs, ODMs, and so rack shipments have been delayed. And it's primarily because this 200 gig issue, and I'll get to that later. But everyone else is racing to get to 200 gig as fast as possible, right? Broadcom just started sampling their switches that use 200 gig, and all the AI ASICs will be implementing 200 gig SerDes very soon. This is very important because it literally doubles your bandwidth per chip effectively. And as we go to the next generation, NVIDIA's talking about putting 400 gig in their next generation chip, right? And currently, like the Ethernet Consortium and all these other groups are trying to figure out, hey, how do we get to 400 gig, right? NVIDIA will do whatever they want. They don't have to adhere to standards. That's great. But for everyone else, you want to be on some sort of standard. And so, do you go to PAM6? Do you go to PAM8? Actually, maybe for optical versus electrical, those things would be different. There's a lot of debate right now in the standards bodies about what to do for 400 gig, but it's clear NVIDIA is going to try and ship this in like 26, 27, and so the rest of the industry, if the current standards bodies go the way they are, they're not going to be able to ship it until like 28, 29. So there's got to be something that really accelerates the rest of the industry, so everyone's not just on a proprietary stack of NVIDIA. Another aspect is with lasers modulators, right? There's VCSELs, which are really short reach. They dominated over 60% of 100 gig based per lambda, so 400 gig and 800 gig transceivers were VCSEL based, but at 200 gig that doesn't work anymore, right? So now everyone has to turn to EMLs or SiPho using DFB lasers. And so this is very interesting, and the supply chain opens up quite a bit, but the challenges and the costs start to skyrocket, as well as the reliability of these things. And then the other aspect is because everyone is racing up the speed so fast, these DSPs, right, which are conditioning the signal, retiming it, et cetera, become very, very costly in terms of power. Right? The leading edge DSPs now, transceivers now take like 30, 32 watts. If you look at NVIDIA's latest server, they actually water cool the transceiver cages. I'm not talking about the chips that are like generating all the heat, but even the transceiver cages have water cooling. And servers tend to, these servers have dozens, if not more, transceiver ports sometimes, right? So power consumption is really, really challenging. And so the question is, can we remove the DSP? And so there's a lot of work being done to remove the DSP, removing 30 watts per, or removing like 20, 25 watts per transceiver, making it so you don't have to liquid cool that portion of the server, greatly reducing cost and also potentially reliability, because hot optics, hot transceivers are always flapping. It's a very funny thing. Inside the OpenAI Slack, there's a fun story that I didn't mean to tell, but inside the OpenAI Slack, every time training is unstable, they respond with the Flappy Bird emoji. If you remember the game Flappy Bird, where like, you click and it pops and you try and go between the pipes. So why that is because oftentimes optics, right, transceivers that are connecting all these AI servers together will get unstable. They'll start having higher bit error rates. And the word for that is called, it's like a flapping link, right? Because it's turning on and off. It's being closed. The timing is good. It's sending good signal and it's not. And so it's like a very funny meme that like even AI researchers know that like, hey, my training's unstable. Clearly it's like a Flappy Bird. It's a flappy link. And so there's a lot of work being done on reliability here. And then the other aspect is because data centers are skyrocketing in size, the standard in data center optics won't work. So everyone's turning to coherent light optics, which is different than standard coherent optics, which are used in telecom. And they're really targeting that, up 20-kilometer range, roughly, to connect all the buildings on a campus together, because data centers are getting that large. To build 100K clusters, 100K GPU clusters, you need multiple buildings in many cases. To build million GPU clusters, you definitely need that, and everyone's trying to race to build these. So there's a new type of optic being built. Marvell, AlphaWave are really investing heavily, but there's also a couple startups out there that are doing a lot of coherent light stuff. And then co-packaged optics, right? Everyone's talking about co-packaged optics. NVIDIA announced it at their GTC. They're only shipping, on the order of thousands of switches with it by the end of this year. But the requirements are clearly there, right? You don't have transceivers. You bring the optics onto the chip. More tight integration will be much, much faster. The challenge is that packaging this is really, really difficult, right? You could put you could source the PIC, photonic IC, and the EIC separately and put them next to each other, but that actually has a lot of issues, because then you have to, getting the signal through the chip all the way to the optics has a lot of challenges. So what TSMC has done is they've implemented a new technology called COUP, right? It 3D stacks the photonic chip and the electrical chip on top of each other. This is not something that's done in regular transceivers. It's not done really anywhere, but TSMC is adamant that this is sort of the best way to do it, and that's really interesting, because like 3D stacking of chips is really relegated to just a few chips out there in the industry, right? AMD has a few chips, and that's really it, right, for production volume chips. But now TSMC is saying every single co-packaged optics chip, which is going to be every switch, every accelerator in the future, needs to have 3D stacking for the networking side of things, not for the compute side of things. And so NVIDIA said they're going to use COUP, Broadcom said they're going to use COUP, Ayar Labs said they're going to use COUP. So it's quickly become an industry standard, despite the fact it's not even shipped in volume yet, which is also very challenging from the perspective of like Global Foundries and Intel and others who are trying to do co-packaged optics, but not on TSMC stack. So that's also a very interesting aspect of this is the packaging. There's a lot of challenging aspects in the coupling area. I'll skip this just because I think I'm a little behind on slides. Shouldn't have told the story about the Flappy Bird. There's a lot of challenges with regards to modulation as well, right? So the industry standard is Mach-Zehnder. They've been used for decades. Every optical transceiver uses Mach-Zehnder, but the Mach-Zehders are really, really large, and they have really high power consumption. And so everyone's trying to turn to micro rings or electroabsorption modulators, which is completely different. There's a lot of challenges with each of them. Temperature sensitivity, the nonlinearity, thermal challenges are really the biggest, but they're so much smaller. The bandwidth that you can get out of them is way higher in terms of a density edge area. And so while Mach-Zehders have been the standard for the industry, most companies in the sort of CPO world are turning to micro rings or even EAMs. But the big challenge here, I talked about how standard optics are really unreliable, right, with the Flappy Bird. The big challenge with co-packaged optics is reliability, right? If you now have integrated everything into one chip, if one link breaks, is that chip garbage now, or do you try and figure out how to run it with reduced rate? The entire flow, optics are temp sensitive, right? And this is transceivers running 30 watts, right? What happens when you stick it in a 1,000 watt plus package, right? Obviously, very, very challenging things on a design and temperature sensitivity aspect. So those links are could potentially be even more flappy. Now, the counter argument is that the laser is no longer in the package; it's outside, and so you're isolating the lowest reliability component, which is like sort of an indium phosphide laser, and you're integrating all of the co-packaged optics in a sort of silicon design test flow, which is much higher reliability than the traditional optics flow. And then there's aspects around degradation. It's really, really, there's puts and takes, but the biggest risk in sort of co-packaged optics is the reliability, right? And then the other aspect is cost, right? Right now, everyone is pushing co-packaged optics into switching, right, for Ethernet, InfiniBand, et cetera. This has very limited benefits, actually. Right? And I mostly view it as it's a testing ground so that they can actually get up to high reliability, right? But if you're talking about your total, in a standard 3-layer network, 100K GPU design, right? Optics and networking are like 10% of your power. And if CPO is reducing power by like 40%, you're still only getting like a few percent benefit on the entire cluster level while introducing all of these potential reliability problems, right? And if you think about it, like 1 day of downtime on the cluster, right, spread across the whole year will more than make up for any power savings and cost savings. So this reliability thing is really, really critical, and your capital savings are not that large. So mostly view NVIDIA and Broadcom's efforts to put CPO and switches as a testing grounds to get shipments, to get volume out there, to get in-field data, to see what the actual data center is like. Because the real area where CPO actually matters is scale up, right? Accelerator to accelerator, accelerator to switch sort of connectivity. And this is where reductions in cost and power are massive, and increases in bandwidth are potentially massive. Right, 20% or so, right? And that's just on power and cost. The other flip side is you could just, quadruple your bandwidth out of the package, and that would be a huge increase in performance. So CPO, really, I think Broadcom is testing in switches. I think NVIDIA is testing in switches, but Broadcom and NVIDIA really just want to put in accelerators, whether it's through their custom silicon design with hyperscalers or for their own, sort of next generation designs. And the sort of the flip side is copper is not boring. Copper is actually really, really exciting. You would think there's not too much to design there, but because it's so much more reliable and it's so much lower cost, everyone wants to be in copper for as much of the as much as possible, right? And so while AECs were less than $300 million last year, This year, there's over 3 million units, and it's going to be multi-billion dollars, right? And so sort of the size of the active electrical cable market has skyrocketed as well. And so you see companies like Credo and Astera Labs and so on and so forth, really, their stocks have done really, really well because of this, right? And so reliability is high on copper, optical it's really low, but then you have the flip side with reach. But power, remember, copper, if you're not ever converting to optical, it's going to be lower power, as long as you're not retiming the signal and such, right? So this is where sort of NVIDIA's rack architecture is really ingenious, right? They've eschewed the sort of, typical racks are 10 to 20 kilowatts in most data centers, and NVIDIA sped run it to 10x that number for this year's shipments. So a lot of data centers aren't ready. Furthermore, they had to do all this like liquid cooling, but the real sort of key aspect of NVIDIA's Oberon architecture used in Blackwell is that the compute trays and switch trays connect over a copper backplane with 5,000 copper cables. This is also why NVIDIA's had a lot of manufacturing problems. They're getting over those. They're really kicking into gear. People are starting to deploy them, but almost like more than half the problems with NVIDIA's current Blackwell has to do with the reliability of even the copper side. And remember, I said copper is way more reliable than optical, and that's empirically true. But more than half of their problems, a lot of times they'll ship the GPU board and it has to get RMA'd back. They take off the connector from Amphenol, put a new one on, and then ship it back and it works. Or the bit error rates on these are really high. So it's really challenging. And because copper is so much cheaper and more reliable, the architecture NVIDIA's shown for their next generation chip is actually a single rack with hundreds of GPUs, right, rather than 72. And instead of all the GPUs in the rack connecting to switches in the middle, they sort of have this like interesting architecture where there's quadrants of pods, and there's a backplane connecting them all. And this is sort of that backplane, and this is the most exotic PCB I've ever seen in my life, and I think anyone's ever seen. It's like 42-layer PCB. Like the PCB tool, EDA tools can't even do it, right? It's like an incredibly like complicated PCB with thousands of channels, and currently this one that the mock-up they shown is 200 gig, but the one they're actually trying to design is 400 gig too. So it's a crazy design that they're trying to implement. I will talk about data centers and power, right? I mentioned going from 10, 15 kilowatt racks to a megawatt per rack. That Kyber design that I showed was 600 to 800 kilowatts per rack, so a megawatt roughly. And this is really changing data center cooling and power, right? And when you look at the largest cluster sizes, hundreds of thousands of GPUs, gigawatt plus data centers are under construction currently. If you go look at this sort of, this is an Amazon data center. In 9 months, they've put up all these data centers, from on the left to the right. And this is going to house a 500,000 chip cluster from Amazon for Anthropic, right? Trainium 2. So their own in-house chip, and they're building a 500,000 chip cluster here. And so while power per chip has skyrocketed, also cooling is very important to that, right? I'll sort of skip over some of this stuff because I'm a bit behind. But yeah, cold plate design, there's some interesting stuff going on there. So how do we cool this and how do we deliver power? That's actually the really interesting thing, because it used to be that chips took, you would deliver 12 volt power to the board, and there'd be VRMs that convert it down to 1 volt DC. But now things are changing rapidly, right? Instead of delivering 12 volts to the board, you're delivering 48 volts. That happened with the Ampere generation of NVIDIA's GPUs, and everyone sort of has adopted that. But now that is causing a lot of power loss, right? If you talk about, hey, I have a megawatt rack, and I'm trying to deliver 48 volts to it, the amps are ridiculous, right? One, like you're just going to have so much resistance loss, and then the other aspect of this is that GPU loads are literally like blowing up grids. So when you look at a standard AI workload, the power fluctuations aren't that large. But in AI workloads, right, if you're training, for example, you're computing a bunch, and then you're synchronizing the weights, and you're computing a bunch, but when you're synchronizing the weights, the compute's not running, and so power just oscillates like crazy, and so the transients like blow up stuff. And funnily enough, Meta, I don't know if they accidentally open sourced this or not, but they're very into open sourcing a lot of stuff. They have this flag in PyTorch, which when you're training, instead of like when you're exchanging the weights, instead of instead of like letting the compute run idle and then causing all these transient spikes, they actually implemented a flag that just has it compute fake numbers, right, during that communication stage. And they named this flag, whatever engineer at Meta named this flag, PyTorch.powerPlant no blow up. Right? And it's basically so the power plants don't blow up, because they did blow up some transformers. They didn't blow up a power plant, but they did blow up some transformers and such, a substation by training, and so they added this flag. And so this is causing like really challenging things. Louisiana, 100,000 homes went out of power, and the suspected blame was an AI training workload from Meta, but we're not sure. There's a lot of interesting aspects happening here. Companies like Tesla have said, you know what, I'm just going to throw a ton of Tesla battery packs. And so if you look at Elon Musk's data center that's pictured on the bottom in Memphis, Tennessee, he has one of the largest battery pack sort of deployments just to stabilize the load. And they're doing this in Texas as well. And so the power problem here is very interesting. This has design implications across the stack. Chip level power delivery is also changing a lot. People are turning to vertical power delivery, which is interesting because now not only do you have to model how the power gets into the package, you also have to model the thermal on both sides, and you have to cool it on both sides. So this is interesting challenges for vertical power delivery, and that's being implemented very soon. The other aspect is 48 volt is too many amps, so people are going 800 volt DC directly. And what's interesting is that they want such high density of compute so they can stay in copper that they pulled all the power delivery out of that rack and are putting it in a separate rack. And the separate rack connects directly over with 800 volt. Now, what's interesting is like this is NVIDIA's next generation design with Rubin called Kyber. But OSHA, right, the sort of like Occupational Safety Health Administration, it's illegal for people to work around these things. So this is their next generation design to increase performance, but literally like you can't even deploy this in many jurisdictions because 800 volt will kill human beings. And I asked NVIDIA about this. They're like, yeah, like robots will like do the maintenance and servicing. It's like, you need the current generation AI to design the robots and like all the AI for them to like be able to even deploy and manage the next generation chips. So I think it's a really interesting circular aspect of this. And gallium nitride is really hitting into gear now. NVIDIA announced an alliance for GaN. Infineon is building 300 millimeter GaN fabs. And many other firms are as well, because silicon can't support the efficiencies required for this level of power delivery that NVIDIA wants. And so there's a lot of work going on with GaN, and that's a new material coming in. Everyone was really excited about silicon carbide, but Wolfspeed, the largest silicon carbide firm, is like almost bankrupt. And so like obviously that's not been playing out really well. But GaN sort of seems like it's hit a stride, and there's humongous investment across the ecosystem for GaN. The other aspect is there's sort of this debate around plus minus 400 volt, which is what Meta and Google want, versus NVIDIA just wants 0 to 800. It's a debate that I don't have time to get into. Same with this, GaN versus silicon. I think the last bit of the presentation that's really, really important is all the way on the token side, right? Why do we need to do all these things? Well, yes, the demand of AI is going crazy. We've all seen a chart that says demand for AI is going crazy. But there's also a cool sort of thing happening with regards to how these workloads are getting scheduled, right? And so when you're running inference, there's actually two main phases. There's prefill, there's decode. Prefill is sort of calculating the context of what the model sees and then into the KV cache, and decode is actually generating each token. And so the idea, it's called prefill disaggregation or disaggregated prefill, is to separate these workloads entirely. And now there are companies making not inference chips, there are companies, including hyperscalers, designing chips for separate prefill and decode regimes, right? Even though those are both inference, they'll have two different chips for this. So it's actually quite interesting that the workload has evolved to the level where people are designing different chips for this. And the basic thing is, DeepSeek open sourced this, but they have four nodes, four 8 GPU nodes, right? Roughly $1 million, right? For these 4 GPU servers, running prefill, right? Calculating the prompt, and then they have 18 servers running one replica of the model for decode, right? Generating the tokens. So this is 22 servers, right? Something like 190 GPUs or so. for running inference of one replica of the model, right? No one runs inference in a single node for leading edge models, right? That's not what people are focused on. And that's sort of what traditional serving is, but with this disaggregated prefill decode, with sort of everything that's needed to be done with the size of models increasing, with the throughput that's required, with the level of batching together users to achieve cost targets, it's really, really difficult to continue to see a world where one node serves a model, right? And so one server even, or even one rack, right? Even one rack's not gonna be enough to serve a model, right? DeepSeek on Hopper is running like roughly 190 GPUs, right? And that's their current generation model. Blackwell is 72 GPUs, it's roughly the same as 190 GPUs, but that's like if the model freezes, right? Models aren't freezing, they're continuing to develop. So even a single rack is not the deployment size for inference. And so the other aspect is, because there's so many different requests coming in, whether it's a chat application, it's a code base, it's retrieval of documents, there's all this KV cache for these different aspects of this chain. But GPU memory is very constrained. HBM is way too expensive, $15 a gig. And then once NVIDIA throws their margin on it, it's $100 a gig. It's really manage all of this KV cache. So now there's layers of software, and this is something that NVIDIA's been building, but all the hyperscalers sort of like OpenAIs and DeepSeeks of the world have built their own level of this. It's called KV cache aware routing. So you have a data center with a bunch of GPUs, and they have different chunks of your code base, of your documents, et cetera, your conversational history, and then you'll have a request come in and you'll route it to a specific GPU a replica of the model, right? Which is, let's call it 190 GPUs. And it'll determine based on the load balance of the GPU server, as well as what amount of the KV cache is still there, right? So they don't have to do the expensive prefill step, right? And so there's these challenging things with regards to routing workloads around data centers as well. And then the other aspect is, everyone's turning to mixture of expert models, and these models, you don't know ahead of time where they're routing, right? The router within the model, in between every single layer, decides where it should route to next. So it'll ping pong all around the model, and you don't know what server it's going to, so the routing of this is, again, very, very difficult, which is why all this crazy high-speed networking is important. And so, how you efficiently route tokens, how you dispatch this, how you do the latency, it's really hard to simulate, but you have to try and simulate it, again, for networking, for system co-design. The design flows here are very, very complicated, and the EDA tools and simulation environments are not capable of simulating, thousands of cycles of hundreds of GPUs, right? So there's got to be a new approach, because people are just sort of like, because they're just sticking their hand in the finger in the wind, because they're not able to actually simulate this ahead of time. Right? So the design flows here are really challenging. And there's all sorts of optimal ratios of what you want to do. Again, don't have too much time. Last thing I want to talk about is sort of scaling larger, right? Because I was talking about hundreds of GPUs and thousands of GPUs for inference, right? For training, this is a significantly higher number, right? I mentioned optics are really unreliable. Time between failure for a transceiver is 5 years. That's failure, not hey, it flaps, right? But that's just hardcore failure. A 500K GPU cluster with with the current ratio of optics that people have today, just pluggable transceivers will fail every 5 minutes so you have to think of some new way to do this. And if you bring it CPO where the number of optics skyrockets, even if they're more reliable, even if they're 10 years, right, you end up with between each failure rather than 5. CPO could be more reliable, but then the end cluster reliability is way lower. So you need new strategies for fault tolerant. Meta just open sourced a fault tolerant training library recently. If you're interested, you should check that out. The other aspect is that because these clusters are becoming so large, right? Meta's largest cluster that they're building right now is 2 gigawatts in Louisiana, and there's bigger plans besides that. Microsoft, I think, has signed over $10 billion of deals with the largest fiber providers like Zayo and AT&T, and I can't remember the other one. But Corning, who is the maker of a lot of this fiber, one order was 50% of their production capacity for 5 years. Right? It's like, this is one order. So they're going to ramp production capacity and such, but it's like this one order was just for connecting a few clusters together for training across data centers. So gigawatt data centers with million GPUs being connected to other gigawatt data centers with million GPUs, because 2 gigawatts, like I mentioned in Louisiana, is more power than the entire city of Philadelphia consumes, which is like a top 10 city. I think it might be like 6 or 7. So the requirements here are really difficult. And Stargate, like sort of the first chunk of Stargate is roughly $50 to $100 billion in Texas, but they've got multiple chunks that they're trying to also connect together like this. And their goal is $500 billion, or at least that's what they've publicly stated. And so if we're talking about one chunk of it is more than a gigawatt in one place, they're going to have many of them connected together. How do you model this? How do you make this happen reliably? How do you design this? Very, very challenging. And so one of the things people are focusing on is asynchronous training. I have a whole report on this, not enough time to talk about it. Yes?
Talk to us how you would approach analyzing the China market differently.
The China market is really challenging because they've like in terms of this cadence, so there's a lot happening on that front. Means it's even harder to see what they're doing. With the tool ecosystem, likewise, right? It's really companies like SideCarrier, which is a Huawei subsidiary, are dramatically ramping up their production. It's really challenging on data centers because it's not like a regular data center. They can just stick it in like an aluminum mill, which consumes gigawatts of power. So there's a lot of challenging aspects with how to analyze it, but currently they still rely very heavily on foreign EDA, although that looks like it's going to be shut down soon. They still rely quite heavily on foreign production, not for everything, but for some things, right? Like for example, wafers and memory. And then lastly, they also rely really heavily. What's nice is that China actually open sources way more software than America does, right? Like the Triton distributed library for map moles is by ByteDance, right? And it's like, okay, well, you don't want ByteDance to get GPUs, interesting, which makes sense. But like, there's a lot of open source stuff out there. The other aspect is consumables, right? Photoresists, chemicals, etchant gas, precursors. All these things are also come from Japan mostly. There's some avenues of tracking China, but it's actually very, very challenging. And what's funny is like a lot of like analysts of China semiconductors, including ourselves, just like look at a bunch of WeChat groups and like forums. But then like you've looked at Reddit or you've looked at Twitter, there's a lot of nonsense on there. So it's really, really hard to analyze China.
Thank you.